What problem does reinforcement learning from human feedback, RLHF, aim to solve in the context of aligning large language models, LLMs, with human values and preferences?
Reinforcement learning from human feedback, RLHF, aims to solve the problem of integrating human preference signals into machine learning methods, specifically in aligning large language models, LLMs, with human values and preferences. RLHF addresses the challenge of incorporating human feedback to guide the training of LLMs, ensuring that the models generate responses that are more aligned with what humans prefer or value. By utilizing a preference oracle and modeling human preferences through approaches like the Bradley-Terry model, RLHF bridges the gap between the learning objective of LLMs and human reward maximization. The goal is to improve the quality of responses generated by LLMs by leveraging human feedback in the training process.
How does the preference oracle work in RLHF, and what is its mathematical definition?
The preference oracle in reinforcement learning from human feedback, RLHF, works by providing a preference signal between two responses to a given prompt. Mathematically, the preference oracle is defined as follows. There exists a preference oracle AP, x times A2, 0, 1, and we can query it to receive the preference signal, where a beer, T, is a Bernoulli distribution with parameter T, and y equals 1 means a caret 1 is preferred to a squared, and y equals 0 means that a squared is preferred. This means that the preference oracle assigns a probability of preference between two responses given a prompt, allowing the RLHF model to learn from human feedback on response preferences. The preference oracle plays a crucial role in guiding the RLHF model towards generating responses that align with human preferences and values, ultimately improving the model's performance in generating more preferred responses.
What are the theoretical benefits of using the Bradley-Terry model and the KL regularized target in RLHF?
The theoretical benefits of using the Bradley-Terry (BT) model and the KL regularized target in reinforcement learning from human feedback (RLHF) lie in their ability to connect the learning objective of RLHF with reward maximization. The BT model provides a ground truth reward function that allows for modeling preferences in a way that is mathematically defined and can be optimized. This model satisfies the Bradley-Terry equation, which helps in understanding and quantifying preferences between different responses. On the other hand, the KL regularized target introduces a penalty coefficient that helps in optimizing the learning process by balancing exploration and exploitation. This regularization term ensures that the policy updates are not too drastic, maintaining stability in the learning process. Overall, the BT model and the KL regularized target work together to provide a structured framework for RLHF, enabling efficient learning and alignment of models with human preferences.
How are previous RLHF algorithms categorized, and what are the challenges associated with deep RL-based approaches like proximal policy optimization, PPO?
Previous RLHF algorithms can be categorized into two main groups: deep RL-based approaches using proximal policy optimization, PPO, and offline direct preference learning approaches. The deep RL-based approach involves training a reward model in the first stage based on a preference dataset, and then using methods like PPO to optimize against a regularized reward. The challenges associated with deep RL-based approaches like PPO include the need for extensive efforts in hyperparameter selection and code-level optimization, especially when fine-tuning large language models, LLMs, due to their computational expense. Additionally, using PPO requires loading multiple LLMs simultaneously, which can strain GPU memory, particularly for resource-constrained open-source projects. On the other hand, direct preference learning algorithms, while easier to tune and requiring fewer computational resources, face challenges related to learning from finite offline datasets, leading to potential over-optimization issues due to incomplete coverage of the prompt response space.
Can you explain the process of online iterative RLHF as outlined in the paper?
The process of online iterative reinforcement learning from human feedback, RLHF, outlined in the paper, involves updating policy pairs based on historical data, collecting new data iteratively, and enhancing the policy performance through exploration and exploitation strategies. Initially, the main agent exploits historical data to update the policy, aiming to learn the optimal policy under the maximum likelihood estimation (MLE) of the historical data. Simultaneously, an enhancer policy explores areas of uncertainty relative to the main agent's policy while maintaining a moderate KL divergence. The enhancer policy assists in providing new information for alignment. The process involves hybrid batch learning, combining offline and online data, and a non-symmetric structure to balance exploitation and exploration. Various heuristic implementations for exploration are discussed, such as adjusting temperature and training steps and rejection sampling. The model is trained using direct preference optimization, DPO, on historical data to approximate the optimal policy under the MLE. The exploration policy is designed to maximize policy differences while maintaining moderate KL divergence. The process involves strategic exploration methods to ensure efficient and stable training, leading to improved model performance on conversation quality and academic benchmarks. The model's responses are evaluated using standard benchmarks like ALPACA-EVAL2, MT, Bench, and Chat Arena Hard, showcasing the effectiveness of the online iterative RLHF approach in enhancing model capabilities.
What are the main results achieved by the model SFR iterative, DPO Llama 3 to 8BR in the evaluation on standard benchmarks like ALPACA-EVAL2, MT, Bench, and Chat Arena Hard?
The model SFR iterative, DPO Llama 3 to 8BR significantly outperforms other open-source models with less than 10B parameters on conversation and instruction, following benchmarks like ALPACA-EVAL2, MT, Bench, and Chat Arena Hard. It consistently outperforms the vanilla offline DPO baseline, showcasing the advantage of online iterative RLHF. Additionally, the model surpasses larger models aligned by DPO or PPO, such as Tulu 2 DPO 70B and GPT-3. 5. Turbo 1106, demonstrating the effectiveness of online iterative RLHF in adjusting the style of model responses and improving conversation quality. Furthermore, the model shows competitive performance on academic benchmarks like GSM-8K, MMLU, Truthful QA, and ARC, with some cases outperforming the SFT baseline. The results suggest that the iterative DPO alignment helps leverage the model's increased capacities injected during pre-training and SFT stages more effectively, showcasing the model's enhanced reasoning and calibration abilities.